I'm Aditi and today I've brought you a very important chapter of physics from class 10th, which is of course human eye and the colorful world. Why is it important? Well, you have studied light. We have studied light. We did the numericals. What we did was studied ray diagrams, how the image is formed and all, etc. etc. Now, there was one question, ma'am, why are we studying this? This is why we studied that. We are going to see a lot of topics that we studied in light with the applications of those topics in this lecture. Now, it's a very interesting, very wonderful, lovely chapter and we might overlook it because it's a small, chotu chapter, but it's very important because we study some defects of our eye which often comes into the exams very frequently. So, do not miss this. Watch this lecture with a very chill, calm mind. It's a very easy, light going chapter. Now, of course, a lot of you watch animes, I know that. So, you watch these colorful, beautiful eyes. How are these lights have different colors? How are these eyes have different colors? I recently went on a small trek and we went there for watching the sunrise and sunsets, and I wondered, it struck me, why these, like, we know that sun gives white light and earth gets its light from sun, but it's white. Then why am I seeing blue sky? Why am I seeing that pretty pink sunset? Why am I seeing that red, orangey sunrise through the clouds? What is exactly happening? Why the white light that comes from the sun turns into red? What kind of magic is this? This is what we are going to study in this chapter. It's not magic, it's our physics. Now, what we are going to study in this lecture will be our basic human eye and its parts, power of accommodation, very important topic, defects of vision, again very important topic, dispersion of white light, formation of rainbows, and atmospheric refraction and scattering of light. And these are some silly topics maybe, but they gives us those pretty skies. So keep watching. Now, our human eye, we will study why we see light because of our eye. So human eye consists of a lots of things. If you see in your eye, you see those brownish blackish parts. Some has blue, some has green. You see the white part, you see the black part, and then you see some eyelashes, but that's not what we are going to study. We are going to study our human eye today and its different parts. What are their functions? What happens if any of that part is missing? Right? What if this white part is missing? What if the black part of the eye is missing? Let's study. So, the first is, if you open your eye and you try to touch that with your finger, okay, don't do it. It's very unhygienic, very unhealthy. But if you do that, because you don't listen, if you do that, the first thing that you touch, the first liquidy, watery thing that you touch is our cornea. What is it? Now, you see it's like a bulge outside, like a dome-shaped layer on the front of our eyeball. So, that is cornea. What is it? Cornea. What is its function, ma'am? So, the basic function of cornea is the white light is coming right. So, it just absorbs it. It refracts. Because it's liquidy, so its refractive index is different than air. So, it refracts or bends our light that is entering into our eye, and it also helps to focus it on the lens, which we'll study later. Now, if it's missing, what will happen if it's missing? If it's missing, our eye will lose its focusing power and the image formation will also be a bit blurry, or there will be no image. Now, cornea is the only part of our body. In our whole body, the cornea is the only part where there is no blood supply. There is no blood supply in our cornea because it takes that oxygen directly from the air, because it's in direct contact with the air, so it does not need any blood supply. Next, the next part, when you see, now in that white part, you see that brownish part, okay? There's a big round kind of thing that is brownish, or some has blue, some has green, some has black, pure black. What is this? It is the colored part of our eye which is surrounding our pupil. Now, let me tell you what pupil is before. So, pupil is, if you see in between that brownish part, there is one black, small black part which is kind of an opening. What is it? What is it used for? So, it basically, that is the exact part which basically allows the light to enter into our eyes. Sorry. So, if that's missing, if we don't have any pupil, so light would not enter into our eye. Light needs an opening, right? So, light would not at all enter into our eyes and we wouldn't be able to see it. Now, there is one very interesting thing. Now, if I shine a lot of light, a flashlight into your eyes will start paining, you will squint your eyes, right? Why? Because there is a certain amount of light that can enter into the pupil. Now, if you shine more light than it can handle, of course, it will get some pain, it will feel some irregularities, disturbances. Now, what happens? When you shine a lots of light, the size of that black part, black part gets smaller so as to control the amount of light that is entering into it. If you go into a dim room, okay, there is no light in that room, maybe a small opening or something. When you just enter into the room, you must have realized when you go for playing, okay, and you come back and you enter into a room and your mom is sleeping, so the light is off. Now you enter into the room and suddenly for 10 seconds you can't see anything, okay, the room goes completely black. Why you can't see anything? Because the size of the pupil is so big, it's getting too much light, and then suddenly you enter into a black room and you can't see anything. So what happens is, then when you enter into a black room, the size of the pupil gets smaller. And then after some time it gets accustomed to the dim lighting and all, and it starts to capture the dim light. Of course, the vice versa is also true. When you are in a black room, okay, and you go directly into the sun, your eyes start paining, right? Because the opening of the pupil is very small, and suddenly you shined so much light into it, so it cannot handle that. So you squint your eyes, you give some time to your pupil, and hence it gets larger so as to get more light. Now, this phenomena that the pupil is getting larger, it's getting smaller, this is what is controlled by our iris. Iris is the part which controls the size of our pupil, and it adjusts there and adjust the light entering into our eye. It's like a camera shutter. It closes, it opens, like that, okay. So, if it's missing, too much or too little light might enter our eye and vision would be painful. Again, when we go into the sun, it pains our eyes in too much light, right? So, the vision can be painful or completely dark in bright light. Now, everyone's iris pattern is different. So, such like we collect thumbprints, right? Or we do signatures, but we collect thumbprints. So, everyone has different thumbprints. Similarly, everyone's iris impression is different. All these 8 billion people on our earth has different iris impression which can be used as a biometric security. That is, the iris impression is what we use when we open our face IDs. It captures the impression of our iris. That's why your friends or your mother can't open your phone. Okay. Pupil, a very interesting fact about pupil is that our pupil, again, it gets lighter or dimmer, that I told you. Okay, next are us aqueous humor. What is this? Some kind of humor thing? No, you don't have any humor. Maybe you do. Okay, aqueous humor. What is it? That we have cornea. We studied about cornea, right? And we also know that our eye also has a lens. Of course, it has a lens. So, this is our cornea, and there sits our lens. This is the cornea, this is the lens. Now, there is a liquid between these two. What is it? A liquid between these two which prevents them from friction, nourishes them with the minerals and all. So, this liquid is what is called aqueous humor. What is it? Clearly watery fluid between cornea and our lens. It maintains the shape of our eye and nourishes cornea and lens. If missing, what will happen? Our eyes would collapse because there is so much friction. There is nothing to keep the eyes and the cornea, the lens and the cornea intact in the shape. So the eyes will collapse, it will lose its shape, and we will have a blurred vision because there is nothing which is keeping the lens intact, keeping the lens nourished. Now, this aqueous humor is constantly being changed, is constantly being renewed after every 90 minutes. Okay, so this watery liquid that you have in your eyes is constantly being renewed after every 90 minutes because it gets dirty, it's in direct contact with our air. So there are dust particles and smoke particles which can harm our eye. So it continuously gets changed. Next is our crystalline lens. Now, what is it? A transparent, flexible, convex lens behind our pupil. So, when light enters into the pupil, where does it go? It hits our lens. What is it? Of course, it's transparent. Flexible, very important keyword. What is it? Flexible. Keep that in mind, we'll come back to it. Flexible, and we know it's a convex lens. Then, what is its function? Of course, to focus the light on a screen. Now, when you see something, of course, that image is being created on something, right? So, our focus, our lens helps to create that image exactly on that screen where it need to be. The lens focuses the light rays exactly on our screen, on the screen of our eye where it should be focused so as to see that light, correct? Now, if it's missing, what will happen? Of course, no light will get exactly focused onto the our retina, which is our screen, and the image might be blur. It's like a camera without focus. You adjust the focus of the camera, right, so as to get a clear picture. If you don't adjust the focus, what will happen? The picture will be blurry. So this is the exact use of that lens in our eye. A very interesting fact is that our lens, what I said that lens is flexible. How it's flexible, I will study about that, but it changes its shape more than 20,000 times in a day. In one single day, our lens is getting smaller or it's getting bigger in one single day, more than 20,000 times. Isn't that interesting to see? So it lets us to see the far objects or the near objects clearly. Okay. Next part is our vitreous humor. What is it? Now, this is our eye. Okay. So, what was this? The front part was our cornea. Okay. This is our lens. Which lens was it? Convex lens. What else did we study? We studied this is the opening. So, this is what it is? Pupil. Correct. So, and what the pupil is held by what? Held by what? It's held by iris. Correct. Okay. So, we studied about pupil, cornea, lens and iris. Now, after this lens, coming behind the lens, what is it? There is, now our eyeball is kind of a round shaped. Okay. What is giving the eyeball that shape? This is just like we studied aqueous humor. This is vitreous humor. What is it? Vitreous humor, aqueous humor was between cornea and our lens. Vitreous humor is between lens and retina. Retina is what? It's just a screen where the image is being formed in our eye. So, it's a clear gel filling the space between lens and retina. What it does? Now, that round shape is being held into that place by this vitreous humor and it allows light to pass to the retina. If it's missing, if the liquid is missing, what will keep the eyeball shape intact? The red eyeball will. Okay, so this vitreous humor is important. It's like a jelly-like substance which makes up almost 80% of your eye volume. If your eye is like this big, 80% of that, 80% of the volume of your eye is being is being filled by vitreous humor. Great. Next is our ciliary muscles. What do you call it? Ciliary muscles. Now we have a lens and it is changing its shape. If this is some jelly-like substance or some rubber, I have to use my both hands to change its shape, right? So if the lens is flexible, again it needs something to change its shape, correct? What changes its shape is our ciliary muscles. So muscles that holds our lens into place and changes its shape is called ciliary muscles. It helps the lens to get thicken, it helps the lens to get thin. Now, if it's missing, what will happen? The lens will not be able to change its shape. The lens will not be able to keep that shape, or it won't be possible to keep the lens in that particular place or shape, because ciliary muscles plays a very important part in keeping our lens at that point, at that shape, at that size, which is very important to focus the image on the screen. Very good. Next. This muscles work automatically, so you never feel them that they're working, that they're contracting, that they're like, just like you can hear your heartbeat or you can hear your nerves, your pulse, you don't hear your ciliary muscles changing shape or working or compressing or decompressing the lens. Okay. Next is our retina. Now I'm talking a lot about retina, screen. What is it? It's just a screen where the image is being formed in our eye. But it also contains some light sensitive cells. What are these? These are called rods and cones. Now, these rods and cones are light sensitive. Light sensitive meaning that when light hits those cells, they will get active. And what will they do is, they will convert that light into electrical signals, which convert that light into electrical signals, and then they pass those signals to the optic nerve, which we'll study just now. Now, what it does is converts light into electrical signals for the brain. Now, if it's missing, no image is formed, there won't be any screen. If there is no screen, the image won't be seen. And retina has these rods and cones. Retina has 120 million rods on your small eyeball. There are 120 million rods and 60 million cones, which helps you. These are the babies which help you to see this beautiful world around us. It converts that light into electrical signals for our brain. Next, optic nerve. Now, optic nerve is a fiber. It's a bundle of so many nerves. You have seen a image of a nerve, right? It's a bundle of so many nerves. See, these are just like this. Bundle of so many nerves which connects our retina, our eye, to our brain, because of course our brain is seeing the image. It is depicting whether I'm looking at the camera, I'm looking at you guys, I'm looking at this board. What decipher that? Brain deciphers that, and for that brain needs electrical signals, which optic nerve passes from our eye to the brain. Now, its function is it carries electrical signals from retina to the brain. If it's missing, the image will be formed on retina, but what will we do with that image? I won't be seeing, I won't know that this is a board, I won't know this is a stylus. Great. Of course, you will have a healthy eye, but there will be no sight. No, like a camera with no cable to connect to a display screen. You have a camera, you click the photo, but you can't see the photo. What's the point of that? Then, this image formed, what is it? The image formed on retina is it's a very important, very interesting. Now, we have a convex lens. We have a convex lens in our eye. And we know convex lens forms what kind of image? It forms real and inverted image. But ma'am, if it forms real and inverted image, does that mean I'm teaching you upside down? Does that I'm standing on my head and my legs are in air? No, it's not, right? Because what our brain does is, our brain is very smart. What our brain does is, it flips the image back to erect. The convex lens makes real and inverted image. It flips it back to a erect image. Now you might ask, ma'am, then why does the brain needs to flip? Why didn't just God or this universe just put a concave lens into our eye? It won't need to be flipped, right? Yes, but we also know that the image that needs to be formed should be formed on a screen, and concave lens does not form image on a screen because it's not just only erect, it's also virtual. If the image is virtual, how can that be formed on a screen? We need a we need a real image, but it comes with inverted. So they designed our brain in such a way that it flips the image back to erect. Now, next is our, the eye is done. We are done with all the parts of our eye. So what did we study? First is cornea, then iris, then pupil, then our crystalline lens. In between the cornea and the crystalline lens, there is a liquidy kind of thing which is aqueous humor. Then in between our lens and retina, there is a thing called vitreous humor. Then it was retina, then it was ciliary muscles which are holding our lens. Then it was optic nerve. So these all are the small things that we studied about our eye, and all these comes together to form this small baby that lets you see all this beautiful world, beautiful colors around you. Now remember, I told you that we'll study one thing which is our lens is flexible. How is flexible? What is it? What is the exact concept of our lens being flexible? So that is called power of accommodation. The power of accommodation is the ability of our lens. I told you it switches shapes, okay? So it gets thin, it gets thick according to the need. What is that need? Let's study that need. So first of all, the ability of our eye lens to change its shape, to change its size is called power, to change its, okay, so if it's changing its shape and size, this is a, this is a convex lens. If this is a convex lens and if this is a convex lens, their focal length will be different, right? This has a large focal length and this has just a small focal length, correct? So if their focal length is different, so if we have only one convex lens, it gets small, focal length increases, decreases, it gets large, focal length increases. So the power, the ability of our lens to change its focal length so that we can see far objects or nearby objects clearly is called power of accommodation. Very important. This is very important. Okay? Very important topic. How it works, ma'am? So we also study one more thing called ciliary muscles. Now those ciliary muscles are holding the lens. If we need to stretch a rubber, my hands will do it. If I need to stretch lens, I would go in and stretch it and okay, now I can see far objects. Then I'll stretch it, send it back to its original position and okay, now I need to study, compress it. Now I need to see my friend far by, stretch it. No, that doesn't happen. What part of our eye does that? Ciliary muscles, because ciliary muscles are holding our lens. Now, when we need to see nearby objects, okay, we are reading, so I need to see the nearby objects. So what happens? The lens gets small. The lens gets small for nearby objects. Just remember it. Nearby, so small. Nearby distance is small, lens will get small. So the ciliary muscles control the shape of the lens, we know that. Then muscles, if muscles contract, lens becomes thick. It stretches down, so lens becomes thick. It compresses, so lens becomes thick. Its focal length decreases. Okay, these are some highlighted things. It becomes thick, then focal length decreases and we can see nearby objects. If muscles relax, so there is nothing to compress the lens, so lens will get stretched. So the lens becomes thin. If the lens becomes thin, the focal length becomes large, focal length increases, and thus we can see distant objects clearly. Okay, so what's happening is muscles are relaxing, lens becomes thin. Okay, if lens becomes thin, we see distant objects clearly. If lens becomes thick, we see nearby objects clearly. Understood? Correct? We'll move to the next. Now there's one thing. Ma'am, what is stopping the ciliary muscles from compressing the lens this much that it breaks? Right? Maybe someday ciliary muscles are so strong, you drank some protein powder or something, you did the gym, protein powder did it hit directly your ciliary muscles and it collapses the eye lens. That is prevented. Universe knew everything, that we are some silly people, we don't know stuff. So it has to prevent us from lots of harm that can happen to us. So that is called limit of accommodation. That means the focal length of eye lens can be smaller, can get smaller to only a certain extent. It won't get much compressed beyond a limit, and it won't get stretched after a certain limit. So the focal length of the eye lens cannot be decreased below a certain minimum limit, and also cannot be stretched beyond a certain limit. The lens becomes thicker beyond a certain limit, so we cannot see very okay. If you have your phone in your hand, right, or your laptop, go very near that laptop and comment down what you see. Do you see clearly? You see that, yes ma'am, I'm some superhero. Even if I place my laptop here, I can read perfectly. No, you can't, right? Why? Because your lens cannot be compressed after a certain limit. Okay, and because it cannot get compressed after a certain limit, it cannot read very nearby objects, it cannot see very nearby objects clearly or distinctly. That is where a concept comes that, okay, you are saying the lens cannot be get compressed beyond a certain limit. So what is that limit? That limit, my friend, is what we call a near point. That is the least distance of distinct vision. Remember this, what is it? Least distance of distinct vision, meaning the least distance where an object should be placed so that we can see it distinctly and clearly. So for our normal eye, it is 25 centimeter. You can, when you read, do not place your notebook or your phone or your laptop near than 25 centimeter from your lens or your eye. And far away, it's just infinity. We just give a basic way concept that we can see till infinity. Of course, we cannot. A lot of people have spectacles these days. They definitely cannot. But even if they did, the Arjun also cannot see till infinity. Yes, he can see very far, but infinity is a beyond point. So infinity is what we call the largest distance that we can see. So farthest distance up to which we can see clearly, and it's infinity. The far point is infinity for a normal human eye, and the near point is what? 25 centimeter from our eye. So near a normal eye cannot see objects beyond closer than 25 centimeter. Next is our defect. Now I'm wearing this spectacle. If I take this out, I might won't be able to see, I don't see objects that are very far away. It gets blurry, and a lot of people, you watched too much phone during COVID or your years, childhood. So you might have these spectacles. Now you don't see far objects clearly, but you might have seen that your grandfather, your grandmother use these spectacles only when they read newspaper or something. Newspaper only when they read, only when they use phone. So why? I can't see far by objects clearly, but I can see nearby objects clearly. They can't see nearby objects, or they might or might not see far objects clearly. What is this? what kind of defects are in our eyes. This is called defects of vision, and we'll study about their correction as well. Vision, that our vision is getting defected. What are these? There are three called myopia, hypermetropia and presbyopia. Let's start studying these. First is myopia. So I told you, you can see nearby objects clearly, so it's called nearsightedness. Nearsightedness is I can see nearby objects clearly, but I cannot see far objects clearly or distinctly. So this defect is called myopia, and the person with myopia can see nearby objects clearly but cannot see distant objects clearly. Correct? Now, there is one thing that is, let's see the physical significance of it. So, understand myopia in this way, that I cannot see objects at infinity, but I can see objects at 10 meters, let's say. So, what is happening? My far point of a normal eye was infinity. Now, it has changed to what? I can see 10 meters, so it has the far point changed from infinity to 10 meter. Correct. Okay. So, what we can say, the person with this defect has far point nearer than infinity. Correct? Nearer than infinity. So, what is happening? The image of a distant object is that should be formed on retina. Instead of forming on retina, it is forming somewhat before the retina, which is, we can say, before retina we had vitreous humor. So somewhat we can say the image is being formed not on the retina but before the retina. The rays which should converge on the retina are not converging on the retina, but instead converging before it. They are not even reaching the retina, they are not focusing on the retina. Okay, so the image of distant object is formed in front of the retina and not on the retina itself. So why this defect happens? So basically the shape and size of your eyeball from your birth till your death, it remains same. It doesn't grow. Your eyes have, you must have seen that children have very big eyes. That is because their head is small, but the eyes, the shape and size of the eye is always remains constant from your birth till your death. It remains constant. Now, why does this happen that the image starts forming in front of the retina? Maybe your eyeball got enlarged. Why? It can get enlarged due to multiple reasons. Some are unknown, some may be because of some accident or something, it can get enlarged. So, excessive curvature, the elongation of the eyeball. Second, excessive curvature of the eye lens. If the eye lens, this shape of the eye lens was focusing light on this retina, but if it increases, so the focal length will increase. So instead of focusing on the retina, it will start focusing behind the retina. Or if it curves down, it curves more than it should be, so it starts forming the image on the before the retina. So excessive curvature of the eye lens is also a reason for this defect. Now the correction is because we need the image to be formed at retina, but it is not forming at retina. What should be done? We use these lenses. These lenses for myopia, in case of myopia, we use concave lenses. Why do we use concave lenses? Because we know concave lens is a diverging lens. I'll show you with this diagram. So let's say in normal eye, this is, let's say, my normal eye. If the rays are coming parallel, they should be focused at the focus, correct? But this is my myopic eye. What is this? Myopic eye. In this, what is happening? Instead of coming from infinity, my eye cannot focus the rays coming from infinity on the retina. What it is doing? It is focusing those rays in front of the retina. This is retina. This part is retina. It is focusing these rays not on the retina but before the retina. And Now this, if instead of infinity, I take my object near the eye. If from infinity, I pick up my project and pick up my object and place it near the eye. So that near point where the eye can see clearly will now be my far point, correct? So let's call this, and no, let's call this our far point. Okay, so our object is now placed at far point of our eye. Now of course I cannot pick up the my object and bring it near my eye every time. That is why we use this lenses. What lens is being used? This concave lens is being used. What it does is, let's say these are the rays that are coming from infinity. So our concave lens diverges these rays. So these rays gets diverged outwards. Okay, and to our eye lens, it appears now that these are the rays. Okay, and these are coming back from a certain point instead of infinity. Okay, the rays were coming from infinity. Concave lens diverged it and sent it into our eyes. Now what my eye lens thinks, that these rays are not parallel. These rays are like this, and they go back and appear to meet at a certain point, which is the far point of my eye. So this is now the far point of my eye. So now again from this far point, the rays will go back into my eye lens, and since when the object is placed at far point, the image is being formed perfectly. So this will be getting focused on the retina and not in the front of the retina. Okay, understood? Next is hypermetropia. Hypermetropia is the one that your grandparents might have, which they cannot see nearby objects clearly, but they can see far objects very clearly. That is why it's called far-sightedness. Now, far-sightedness, a person with hypermetropia cannot see distant objects, can see distant objects clearly, but cannot see nearby objects distinctly. The near point for the person is farther away from the normal point. Now I told you that your near point should be 25 centimeter from your eye lens, correct? If you bring it closer, you won't be able to see correctly. But in your grandparents, what happened is, their near point was 25 centimeter originally. What happened is, their near point shifted further. So they cannot read this now. You are reading your copy from here and the image is blurry, and you are reading from here, the image is perfect. But for them, they are reading from here, it's still blurry. The one that is perfect for you is blurry for them. They have to push it backwards so that they can read it properly. They can read it without any blurring. Okay, so they cannot see nearby objects clearly. Thus their near point shifted backwards. Their near point shifted away from 25 centimeter away from the near point. Okay, yeah. Then why this defect might happen? Of course, again, that in myopia, my eye lens was focusing the rays before the retina. It was focusing these rays before the retina. Now in hypermetropia, what's happening is, my lens is focusing these rays behind the retina. This is our retina. It is focusing them behind the retina, and this can be due to the shortening of our eyeball. This can be because the eyeball became too small, or the focal length of eye lens is too long. The lens became, let's say, if it stretches out, so the focal length increases, and instead of focusing on the retina, the focal length is behind the retina, so the rays will be converged at the focal length of the lens. Very good. So in myopia, we used concave lens. In hypermetropia, we will use convex lens. Why, ma'am? Okay, let's understand again with the diagram. Now, this is my normal near point. Okay, this is my normal eye. This is normal eye without any defect. This is my near point, which is 25 centimeter. From this, ideally, what should have been happening? These rays should be, this is my near point. Ideally, these rays should go to my eye and they should converge at the retina for a normal eye. Now, this is what is happening in here. If I place my object at my near point, the rays are not getting focused on the retina, but they are getting focused behind the retina. Understood? This much clear? Okay. Then, now this is like, see, my normal, my near point was here 25 centimeter. What I said you? I told you that my near point shifted backwards. If I shift my near point backwards, if this is my hypermetropic eye, if I shift my near point backwards, now my lens is able to focus on the retina perfectly. Correct? Here it was focusing behind the retina. If I took this object, placed it far away from the eye, more than 25 centimeter, let's say it's 30 centimeter. Okay, if I placed it at 30 centimeter instead of 25 centimeter, my lens is able to focus the rays on the retina. So, I need to do something. I need to shift my object behind. Okay, so we use, for that we use convex lens. For that we use convex lens. Fine. What is happening? Now, the object is originally at my near point. So, if these rays goes to my convex lens, what it does is, the rays are coming, it converges, convex lens converges those rays. So, it starts to converge those rays. And to my eye lens, it appears that instead of coming from here, the rays are actually coming like this. Okay. If the rays are coming from a far point, it appears to my eye lens that the rays are not coming from this point. These are actually coming from this point. Oh, these are coming from my normal near point, my new near point. So, I will make the image perfectly on the retina. So, the image forms perfectly on the retina. Clear? So, in myopia, we use concave lens. In hypermetropia, we use convex lens for the correction. Next, there is one more thing called presbyopia. Now, sometimes there are people who can't see far images as well as nearby images. These are mostly due to the old age, due to the weakening of ciliary muscles, that they cannot hold the lens properly. The lens is not able to focus its shape and size perfectly. And what happens in this, what is happening? The near point goes far and the far point also comes near from infinity. Correct? This is correct. So, our power of accommodation, that is the changing of the ability of the lens to change its shape and size, it decreases with the age because our ciliary muscles get weak. The gradual weakening of ciliary muscles and diminishing flexibility of our eye lens. So, correction for this, for myopia we used concave lens, for hypermetropia we use convex lens, for presbyopia we will use a lens called bifocal length. Bi means 2. Bifocal length is something which has both concave and convex mirror. So, it is like this is your specs, and in the specs there is a small area on the downward side of the lens. So, this particular area is used for reading, because we read downwards. Of course, we don't read like this mostly. So, on the downside of these specs, on this specs on the downside, there will be a which lens? Convex lens, because we need to see nearby objects clearly, and the upper ones will be concave lens, because we need to see far objects distinctly and clearly. This is just presbyopia. So, we did the defects of vision and their correction. myopia, hypermetropia, presbyopia. Myopia cannot see far objects clearly, hypermetropia cannot see nearby objects clearly, presbyopia cannot see both objects clearly. In myopia we use concave lens for correction, in hypermetropia we use convex lens for correction, and in presbyopia we use bifocal lens for correction. Next, now here we have a simple question. A person with myopic eye. Now in numerical, what did I tell you in the numerical video? Read the numerical carefully and write the important information down. Now, so myopic eye, that means the person has myopia, correct? Cannot see objects beyond 1.2 meter. So his far point, they are saying he cannot see objects which are further away from 1.2 meter. So his far point should have been infinity for a normal eye, but now it's 1.2 meter, correct? What should be the type of corrective lens should be used to restore his proper vision? Ma'am, for myopia, you tell me, which kind of lens is used to correct a myopic eye? Comment down right now. I'll see the timestamp. Comment down right now which kind of lens do we use to correct the myopic eye. Okay, moving on. Next, now do you know a fun fact about your eye? Your eyes can live even after your death. They are not zombies. There is no afterlife that I'm going to see that, but they live. Since, see, my cornea is not getting any blood supply. It's getting oxygen from the air. So it keeps getting oxygen from the air. So my eyes keep living even after my death, even after the death of a person, but it will only live for 5 to 6 hours. A medical team will come, will extract the eyes and all, but it's a very good cause. Donating eyes can save like a lots. Your one eye of a person can save multiple people's blindness. Some just require cornea, some just require iris or pupil. So mostly it's cornea. So by donating our eyes after we are no more, we can light a blind person's life. Okay. Next is, now there are some things that we are going to study about certain objects. There are certain phenomena in physics that, now we study refraction, right, in the last lecture of light, and we studied refraction. Now there are some important applications, important discoveries that were made out of that refraction topic. It was made when they saw light, they saw different colors of light. They're like, what is happening? How the white light is splitting into colors and all. And we'll discuss all that in today. Before that, we need to discuss one very important we need to discuss one very important topic, which is refraction of light through a glass prism. Now, what is happening? Just look at this. Let me hit this prism with a ray of light. Now, we studied refraction. Of course, this is rarer medium, this is denser medium, this is again rarer medium. So, my first thing should be making normal to this surface of this prism. Now, it's going from rarer to denser. Ma'am, it will bend towards the normal. So, it bends towards the normal. Then, again a normal at this point. So, this will be a normal. Normal should be made according to the prism length, a prism surface. So, this is normal to the prism. And ma'am, now it's going from denser to rarer. So, instead of bending towards the normal, it will bend away from the normal. So, instead of going straight, it bends away from the normal. Now, this is our incident angle, this is our refractive angle, and this is our emergence angle. Now, if I extend this, if I extend the incident line and I extend the emergent ray, and this is where they meet, is called angle of in glass lab, if you remember, we saw lateral displacement of incident ray and emergent ray. In case of prism, instead of seeing lateral displacement, we see angle of, what we see? Angle of deviation. How much the incident ray got deviated, by which angle the incident ray, it should have been gone like this, but it's going like this. So, at what angle this incident ray got deviated from its original path is denoted by angle of deviation. This is angle of emergence, angle of refraction, angle of incidence. One more thing, this is prism, okay. So, this A is called angle of the prism, okay. This A, this prism can be like this, right, and this prism can be like this. That is true, right? So, depending on that angle, this angle, particular angle is called angle of prism. Then, next topic is dispersion of white light by a glass prism. We studied glass prism. Now, let's study its applications. If you take a prism, I'll probably try to get a prism and show you. If you take a prism and you, like, even if you put that in the sunlight, or I hit it with a white light, what will happen? You will see 7 different colors. You won't just see one white light coming out of it. You will see 7 different colors coming out of the prism, and you're like, what just happened? I put in white light in the prism, and it's giving me 7 different lights. How? So, this is a little experiment we'll do. What happens is, this white light is made up of these 7 colors. Which 7 colors? These. Vib-Gyor. What is this? Violet, indigo, blue, green, yellow, orange, red. So, our white light, the light that sun is giving us, is made up of these 7 colors. All these 7 colors combined together and make the white light. Now, in prism, what is happening? Its refraction is happening. Now, all these colors have different wavelengths. If they have different wavelengths, now refraction will depend on the wavelength and frequency of the light. If these red color has different wavelength and blue color has different wavelength, so the angle at which they will be refracting, will be different. The angle of refraction of blue will be different than angle of refraction of red. And that is why, my friend, when you hit the prism with white light, it will split it into 7 colors. Okay, understood? This is just called the dispersion of white light by a glass prism. The splitting of light into its component colors is called dispersion, and these 7 colors are called component colors of white light. Okay. Next is called okay. How did we see? Okay, ma'am. You hit the prism with white light and it split into 7 colors. But how does that give a reason that white light is being made of these 7 colors? Maybe there is some color which left out, which our eyes couldn't see, and it got scattered in the air, and maybe white light is made up of a new different color that we don't know. So, Newton Baba came into the picture. He was like, let me tell you something. Let me do some experiment and find out if white light is actually made of these 7 colors or not. Actually, he was the one who told for the very first time that white light is made up of these 7 colors. How? So, what he did was, he took a prism. He shined white light onto the prism. Now, we know it split into 7 colors. It split into this red and then violet colors. Then, what he did is, he placed an inverted prism in front of those 7 colors. These 7 colors are coming out of the prism, and he inverted this same prism, he inverted the similar prism and placed it in front of that refracted light, dispersed light. Now, what he saw was blew his mind. He saw that when these 7 colors again entered into the prism, what happened? They rejoined together. this is red, this is violet. They came out as red and violet. When they passed into the inverted prism, when they passed into the inverted prism, came out, the light that came out was not 7 colors, it was just white color. The only white color instead of different red and violet. So, this experiment, let us see, this experiment proves that, what is time? 2. This experiment proves that the white light splits into 7 colors, and if we place the inverted prism in front of it, it will again merge back into white color. Okay, this is how Newton Baba knew that the white light is made up of these 7 colors only. So, what is it? Different colors of light bend through different angles. We studied that with respect to the incident ray. This is the incident ray. They are bending at different angles as they pass through the prism. Red light bends the least. Now, this is something to remember. Red light bends the least and violet bends the most. And the rays of each color emerge along different paths and thus become distinct. Each color in that VIBGYOR, each color emerges through a different path. They bend at each bends at different angles, and thus we see them as distinct colors. Next is our formation of a rainbow. Now, you saw again, you see orange, you see skies, pink skies, you see blue clouds, also you see rainbow. This should be connected, right? Colors in the sky, ye wo. So, what happens in formation of rainbow? Formation of rainbow also uses this concept of dispersion. Rainbow, when we shown that white light into a prism, it got split into 7 colors. There are some tiny droplets in the air when it rains, right? When it rains, you see that the environment around us get more humid. If the environment gets more humid, then that means there are water droplets in our sky. If there are water droplets in the sky, then the refractive index of air and the refractive index inside that water droplet will be different, correct? And white light is of course hitting those water droplets. So, when that white light enters into that water droplet, it will get refracted. That is true until this is true, right? When a white light will enter into that water droplet, it will get refracted. Now, in a rainbow, what happens is, rainbow is just, we know rainbow is a natural spectrum, okay, seen after rainfall, we know that. Why it happens? It happens because of the dispersion of sunlight through tiny water droplets in the air. What is happening? This white light hits our water droplet, and we know every light, every color in the white light, they bend at different angles. So, this is our red light, this will be our red light, this will be our blue light, violet light, okay. Then what happens? This inside that water droplet, okay, inside that water droplet, what happens is total internal reflection. This is a thing you might have studied, you will study later. The total internal reflection will happen, which means now from here also it's water. This is the same surface, right? But instead of going out and refracting out, it doesn't refract. It reflects from the other end of the water droplet, and then from the same end, it refracts out. So, what we see is a colorful rainbow, okay. This is the basic concept of rainbow. So, what is happening? Refracts, it goes and it refracts, it disperses into 7 colors, it is dispersing into its 7 consequent colors. Then, the light reflects internally inside the water droplet. The light will reflect instead of refraction, it reflects and then it refracts again when it exits that water droplet. Then this rainbow appears, this normal fact, this rainbow will always, if the sun is behind you, then you will be able to see the rainbow. The sun should be, it appears on the opposite side of the sun, and you can also see a rainbow near a waterfall or a mountain when the sunlight is behind U, correct. Then we have one more concept called atmospheric refraction. Now, you know refraction. Now, our atmosphere has certain limits. Let me just, we have stratosphere, okay, we have magnetosphere, we have troposphere, I think, I don't know. So, all these layers, in these layers, the ions, the atoms, the particles which are present are of different density. In maybe stratosphere, most of the elements will be there, or different kinds of elements will be there. In magnetosphere, different kind of ions, different kind of atoms will be there. So, the density will be different. If the density is different, the speed of light will be different in them. If the speed of light is different, what will be different? Exactly, refractive index will be different. So, there is a phenomena which is atmospheric refraction. What is this? So, when you light up a fire, okay, whenever you have seen a fire, if you go to bonfires with your schools or your friends, you will see that if you look through the fire, you will see that behind that fire the atmosphere will look like it's dancing, and the air will look like it's dancing, something like this. It's bubbly and it's not clear edges, right? Why this happens? This is what atmospheric refraction is. When you light a fire, the air around it gets hot, and one thing is, the hot air is less dense than the cold air. So, the density of the hot and cold air, here the air is hot, but here might be somewhere far or behind this fire, the air will be cold. Now, the light is passing from cold air to hot air, and then to cold air, and then to your eyes. Then what happens, when the light enters to the cold air and cold air is more dense, then it enters to the hot air is less dense. So, the density changes, refractive index changes. When, let me make this. See, this is maybe a cold air, okay, this is a hot air. Is it visible? Yeah, probably not. Okay, let's say this is our cold air and this is some area of hot air. Now, this is less dense and this is more dense, and it's going from denser to rarer, we can say, okay, and then there is fire here, okay, and this hot air, again there is hot air, and then you will not be standing near hot air, right? You will be standing somewhere cool. So, this is cool air. So, what is happening, light is entering into the cold air, then it's getting refracted again somewhere, and then in the air it's same, and then it's again getting refracted, and then in cold air again getting refracted, again reaching your eyes. So, what is doing? Light in itself is dancing through these airs. When the light is going up and down and like dancing around the hot and cold, dancing between the hot and cold airs, then we can say that is the cause of atmospheric refraction. That is atmospheric refraction. Objects seen through hot air appear to waver or flicker, okay, appear to dance. So, why is it happening? Hot air is less dense. We know hot air is less dense and has a lower refractive index than the cooler air above it. So, temperature is constantly changing, which continues the bending of light, and if light is keep bending again and again, the apparent position of light, the actual position of light source, we can say, keeps on changing, and this wavering is thus a local effect of atmospheric refraction. Now, there is one more thing you must have noticed, that the stars twinkle. Do you think that the stars, which are millions of light years away, are twinkling? They are just like our sun is a star. Does it appear to twinkle? No. But the stars which are too far away from us, they appear to twinkle. Why? Why does that happen? Again, it is a phenomena of atmospheric refraction. What I told you that there are certain layers of atmosphere. Now, let's say I have a star million kilometers, light years away from my earth or my eyes. These are my eyes, okay. This is not my eye. This doesn't look like my eye, yeah? Okay. So, this is a star. Now, what happens is, this light comes here and it keeps on bending, and it bends and then it bends, and then here are some particles, here oxygen, nitrogen, water droplets, and it keeps on bending and then it reaches my eye. So what is happening? Then again the second light which is coming, then it's now there are few molecules here. Okay, now the molecules changed their position because in the air molecules are flying around, right? So instead of this, molecules are now like this. So instead of bending like this, this light will bend towards this, then this, then this, and this is how it reaches my eye. So this bundle of light, this star, the light from this star keeps on changing its position, keeps on coming in a different direction as we see from the this star. So to our eye it appears that first the star was here, then it is twinkling, then it is again the refraction, the light ray because of the refraction changes its direction. So because of all these changes, because of all these continuous change in the direction of bending, it appears that our stars are twinkling. There also one question arises that, ma'am, planets, these planets do not appear to twinkle. Sometimes you can see Venus in the sky, but Venus doesn't twinkle. I don't see, when you look at the Venus, sometime when you have some time, try to look at the Venus. It's very prominent in the sky. So what is happening is you will see a star near it and it's twinkling. But you will see Venus, it's not twinkling. Why, ma'am? This contradicts your whole concept that we see twinkles. What is happening is, planets are very near to us. By very, I don't mean few kilometers, but still if you compare it with the direction of, with the distance of stars from Earth, the planet distance is very less. So to us, the star appears as a point object. The star, it appears to us as a point object. But planet instead, this is, let's say, Saturn. So planet appears as a bundle of stars. It does not act just as a point object, sorry, bundle of points. It does not act just as a one point, it acts as a bundle of so many points. It's not this dot in the sky. It's a big planet in the sky, and because of that, now the light is coming from all these points and entering our eye. Even if it refracts, even if each point of the planet gives us the light which is bending continuously, the light is bending continuously from planet as well. But since it appears to come, so many light rays are coming at one point and hitting our eye, it does not create much difference. The average refraction cancels out, and hence we do not see planets twinkle, but we see stars twinkle in the sky. Next is, what is this? What you have seen this maybe from clouds, maybe when you go into a forest. This is what my chutku friends is called scattering of light. What is scattering of light? When our white light, when our any light, when it hits, now our atmosphere, our around us there are oxygen, my air has oxygen and other particles, nitrogen, carbon dioxide. So when this light hits these particles, it scatters. Instead of traveling straight, there is a particle, instead of traveling straight, it came into its way and it scattered, it bent away. Now there are some conditions. So scattering is the deviation of light. Instead of going straight, there was a particle, it got deviated. Okay, deviation of light from its straight path when it strikes any tiny particles like dust or gas or water droplets in our atmosphere is called scattering of light. Very good. Now this scattering of light gives us a very great concept of Tyndall effect. What is happening is, if you have gone to some treks or in forest, or simply you are in a room and there is just a small window, okay, and light is coming from inside that window, you will see that path lights up, right? That path of Tyndall, that path of the light lights up. You can clearly see the path of that light. In this room, there is continuous light. But if I close all the lights and just open one small window, outside light will come inside and the path will be clearly visible. The dust particles might be clearly visible. The gas, the water droplets might be visible. Why? That is called the Tyndall effect. So, what is happening? The Earth atmosphere is a heterogeneous mixture of minute particles. Okay? Our Earth includes my very small particles and some mixture of those particles, which is smoke, tiny water droplets, suspended particles of dust and molecules of air. So, when a beam of light hits these particles in the atmosphere, hits these fine particles in the atmosphere, they become visible to us. And this phenomena of scattering of light by the colloidal particles, you have studied what colloidal particles is, gives us the rise to Tyndall effect. So, these very fine, now very small particles, which are very fine particles, scatter mainly blue light. Why? This scattering of light depends on something. If my light has this kind of beam and there is this particle, okay, small particle. So, this particle is comparable to this wave. We will say the wavelength of light beam is comparable to the wavelength of the particle in the atmosphere. If both of those wavelengths are nearly equal, the light will get scattered. But if my particle is big or my particle is very small, the wavelength of my particle is very small as compared to the wavelength of incoming beam, or the wavelength of my bigger particle is very small as compared to the wavelength of incoming beam, then that beam will not get scattered. For scattering to happen, the wavelength of beam of light should be comparable to the wavelength of that particle which it's hitting. Okay. So, in our atmosphere there are very fine particles. Now, blue light and red light, we have in white light we have certain number of lights. We have red, and on the other hand we have blue and violet. So, the wavelength of blue light is less than the wavelength of red light. And in our atmosphere, we have very fine particles whose wavelength is comparable to the blue light. Okay, save that information. So, very fine particles. Now, wavelength of blue light is less than wavelength of red color. Okay, wavelength of blue color is less than the wavelength of red color, which means the small particles, the particles which have small wavelength, very fine particles will scatter the blue light, and while the larger size will scatter the red light. Now, we will see some questions that arise from this topic, which is, why is the color of our sky blue? Now, what did I say? My atmosphere, this is my earth. Okay. Now, my atmosphere has some small, very fine particles. My atmosphere has what? Very fine particles. And the wavelength, this is how you denote wavelength, lambda. This is called lambda. My wavelength of blue light is less than wavelength of red light. And these particles, the size of these particles of my atmosphere is comparable, these contain very fine particles. Fine means very small particles. So, the size of these particles is comparable to the wavelength of blue light instead of red light. Because wavelength of blue light is smaller, size of particles are smaller, hence the blue light, this is white light. Okay. So, the blue light gets scattered away. This is the blue light. Do I have? So, it comes till here. This white light came here, and here we have very fine particles, and thus it scatters the blue light all around the earth. It scatters the blue light, and the red light does not get scattered because its wavelength is not compared to the size of particles we have in our atmosphere. So the red light goes straight, or it does not scatter that much, and our blue light scatters in the air in our atmosphere, and hence the sky, the color of our sky looks blue. Okay. Next question, why the danger signals are red in color? What did I say? That blue light scatters away. What is happening? The blue light scatters away. Okay, let's say this is my atmosphere. Blue light scattered away. Okay, what didn't scatter away was my red light. So the red light didn't scatter away. Now if I'm standing here, okay, if I'm standing here, what will I see what will I see better? Blue light which scattered away or the red light? Of course, the sharp color, the danger signs should be very sharp, right? You should have seen them from a far distance, then only you will be able to take some action. So this red light doesn't scatter, it's coming from very far into our eyes, and hence we can see the red light more prominently, more sharper than the blue light, and hence our danger signs are red, so that we can see red color from very far away. That's our red lights are, and traffic lights have red color, we can see them from a great distance, right? But the sky is blue, all the sky is blue, so the blue light gets scattered away, red light does not get scattered away, and thus we can see red light from a far different distance. I think that's it. Okay, there's one question. The near point of a hypermetropic eye is 1 meter. Now, what did I tell you? Write it down. What it is? Hypermetropic eye. Okay. Now, remember, for hypermetropic eye, for correction, I used convex lens. Okay. Now, what they're saying, the near point is 1 meter. So, this is my near point, this is my convex lens. Okay. What they're saying is, what is the power of the lens? What do we need to calculate? We need to calculate the power of the lens. We are writing everything down, okay, to correct this defect. Assume that the near point of the normal eye is 25 centimeter, we know that. So what is happening here? Let's say my object is at 25 centimeter. I need to see that object with 25 centimeter. But at 25 centimeter with my lenses. But that object is at 25 centimeter. I won't be able to see it clearly because my near point has shifted to 1 meter, correct? So this is my 1 meter. Let's say this is my 25 centimeter, correct? Now what our corrective lens does? We studied that, what did we study? Here, we studied that what this convex lens does is, it makes the image, then this is the near point, it hits the convex lens and it appears to come back from it, makes the image again to a far away point, so that it appears to our eye that instead of coming from 25 centimeter, the object is at 1 meter, correct? So that means the eye lens we are using for correction is actually just doing nothing but making the image of the object which is at 25 centimeter at 1 meter, and then this 1 meter will go into our own eye. So this is our object. For this lens, this is our object and this is our image. So what we know, ma'am, u equals to, object is at minus 25 centimeter. Okay, our image distance is minus 100 centimeter. It was 1 meter, and if I convert 1 meter into centimeter, it is 100 centimeter. I need to find the power, and I know to find the power I need focal length, and to find focal length I need V and U, which I have. According to lens formula, I have 1 by f equals to 1 by v minus 1 by u. Both are negative. because both are in, because in convex lens both are formed at the this left hand side. So 1 by f equals to minus 1 by 100 minus of minus 1 by 25, correct? And if you solve this, you will get minus 1 by 100 plus 1 by 25, which will give 100 as LCM, minus 1 plus 4, it will give you 3 by 100, and our focal length then will be 100 by 3, and this is 33.33 centimeter. So our focal length comes out to be plus 33.3 centimeter. That means that for power I need 1 by 33.3 diopter, correct? This is the answer for our power. We have found the value of power that was asked from us. Okay, there is one more question I have for you, that why I asked you in the starting as well. Now you should be able to answer this, okay? Comment down your answers and I'll check if it's right or not, okay? Why the sunrise or sunsets appear blue to us, appear reddish, or pink, appear red instead of white or instead of blue, correct? Also, I have one more question for you that I'll tell you. When you have seen something, when at sunrise, okay, this is our earth, this is the sun. When the sun sets or the sun rises, what is happening is the actual sunrise is happening after 2 minutes than we see the sun. Like we are seeing the sun, but the sun has not passed the horizon yet. And at the sunset, the sun has already been set. The sun already got down from the horizon, but we are still able to see the sunset. So sunset or sunrise is before and after 2 minutes of the actual sunset of the sunrise. Why? Let's say this is my horizon and this is the sun. Okay, it has already been set. Okay, the sun has been set. Now what is happening? There are many layers of Earth's atmosphere. So the light is coming from the sun. It bends. It again bends. It again bends. But to me, the light will appear to come from this point. This is the refracted ray. If I extend it back to my eyes, it will appear that the light is not refracting and coming. It will appear that the light is coming from this point only, correct? It will appear from straight back, and hence because of this reason, because of atmospheric refraction, it appears to us that the sun has already been set. It appears to us that the sun has not been set yet, where the sun had already been set. Or it appears to us that the sun has risen, but in actual the sun has not risen yet. Okay, this is one reason that you can write in your exams for these answers. So here we complete our chapter, which is human eye and the colorful world around us. We studied human eye, the different parts of human eye, which was what? We studied cornea, we studied iris, then pupil, we studied crystalline lens, then we studied aqueous humor, then we studied vitreous humor, then what did we study? We studied ciliary muscles, we studied the retina, and we studied optic nerve. All of these comes together to help us make a very nice image of this very colorful world around us into our brain and helps us to see the world around us. Then we studied scattering of light, dispersion of light through a glass prism. We saw white light is not just only white, it consists of 7 different component colors, which is pure. The wavelength of blue is less than wavelength of red, and that's why it gets scattered by the fine particles in our atmosphere. Then we studied dispersion, scattering, we studied Tyndall effect, we studied, what did we study after that? We studied atmospheric refraction, and we saw different kinds of questions. All these questions are very important. They can come in your exam directly even or with some examples. So make sure you know the basic concept of it, and then we saw 1 or 2 numerical. That's it. The chapter is completed. All the best to you, and subscribe to this channel because we are bringing you lots and lots of good content. There will be lots of videos coming for the lectures, one-shots, important topics, PYQs for all the subjects, not just physics, maths, chemistry, bio, SST and all the topics. So make sure to hit the subscribe button and hit the notification button so that you don't miss anything. The strategy videos are really important. That will actually make you clear the ace your boards, because there is one thing which you need, what you need to study, but how you need to study that, how you should revise it, how you should follow those things that you studied. You keep them in your mind and you write them down in a good manner so that they can get you good numbers. It's very important. Stay healthy, stay good, enjoy your festivals, and a happy Dashera, happy Diwali to all of you, and tata, bye bye, study well.